All right, so we have, as you are aware, been talking about chemical reactions. So when you look at the arrow, that's where you're going to divide your reactions in half. What is everything to the right side of the arrow? And you could look at your handout. There are plenty of examples on page 2 and page 3. If something is on the right side of that arrow, those are products. And there can be just one. You can just have a product only. Okay? We saw that yesterday when you add hydrogen and chlorine together, and it gives you hydrogen chloride. There's two reactants on the left-hand side of the arrow that come together to make one single product on the right side. You can also just have one reactant on the left side that could break down or break apart into two separate products. One reactant into two products. Okay, so this is where we had left off, just trying to get, let's say, an idea of what these reactions are like. And you were tested on that for your student learning objectives, and we will compile the data at a later time. But as you had said, the products, these are what's produced and are on the right side of the arrow. We illustrated this. You could add together all of the different elements together as long as you distribute through your large number of coefficients. So one of the reasons that we want you to have such a good, I don't want to say handle, a good understanding of this, be the right way of looking at it, is because we do an activity in the lab to where you are taking two different types of substances, react them, form a product, and then you can mathematically predict what it is that you are forming and how much should be in there, should it be done correctly. And that's a big part of what general chemistry is. And then there you can do more types of calculations. So we are setting, hopefully, a good foundation for you to learn this content and be successful, whether it's 2 years from now, 4 years from now, 6 years, whichever, as your future awaits you. Okay. So one of the things that we see happening, we talked about candles yesterday. You have the wick in the center, so that continually burns because the candle is the fuel. So as that has the spark, it lights the wick. That creates a little bit of heat, and then that, of course, melts the candle, provides the fuel, and you have open air or oxygen that allows that candle to keep burning. So what we want you to think about here, eventually, what's going to happen to this candle when it's inside this jar? Okay, what is it going to run out of, and what is it going to continually produce? What is it telling you here? What is going to be produced here? Okay, so you go to any type of fire extinguisher that's a gas that's under pressure, and it's actually liquid carbon dioxide. You could look at it in that fashion. There's a little more complex chemistry. For our purposes, that's how we would explain that, is that when you spray any type of small fire with that carbon dioxide, it takes all the oxygen away and then puts the fire out. So in this case, way back when, in the 1600s, okay, Antoine Lavoisier, as you would guess, is a Frenchman. I don't know if I pronounced that right. But within this sealed container, we know that on that triangle, there's three things that need to take place. You need to have fuel, you need to have heat, and you need to have oxygen. So eventually, within this sealed container, all of that oxygen gets consumed the carbon dioxide is left behind, that puts the candle out. Probably you could say the very first type of fire extinguisher, and that's where we could say that this had originated. So, in this case, we had said that sometimes we have, let's say, a reactant, and then you get two products, and this is an example of that, okay? And I don't know if there's a reaction that's similar to this in your handout that you could practice with, but we'll be going over this in just a moment. Okay, does everyone have this content that wants it? Okay, I don't know if you need to take a brief look at the next one. No, we can come back to that. Okay, so let's look at C once what's happening here, okay? And that would be as follows, okay? So Lavoisier had this test tube. It had this red powder in it. So upon heating that, okay, what did it say took place inside of that test tube? So if we had this, we know that was in there, okay? So how would we write this compound out if we're going to make a chemical reaction out of this? What is the symbol for mercury? Okay, so we have some Hg, and then what is your oxide ion? And it tells you that in your handout too, for those of you who are looking at it. It just tells you what it is, rather than just trying. And it tells you that up here too. What is the formula or symbol for the oxide ion? Okay, just plain O. Okay. Are we done writing that compound out?
No.
And maybe, let's maybe determine that. We say, go by which ion first, the negative or the positive side? Always start with your negative side, okay? So of these two, you got a 50-50 chance. Who's got the negative charge? Oxide, because it's on this side. The positive ions are always written first. So what is the charge of one oxide ion? Not -1, not 1. Okay, and you have this information provided for you on the periodic table. It's got a charge of -2. Okay, and then what can mercury have for a charge?
+2.
Is that the only one?
And +1.
Okay, so again, from last chapter, how do we know which one to pick from if there are two different charges?
It shows 2 on mercury.
Yeah, because this Roman numeral here is telling you what the charge is. So it is +2. Does that add up to 0?
Yes.
Yes, it does. So sometimes this happens. It just cancels each other out. Then, since this is on the left-hand side of the arrow, we consider this as a what? Yeah, you can just have one compound as a reactant, okay? So that would break apart. What did he observe? It said he began to see this silvery liquid. And what would that silvery liquid possibly be? It tells you what it is in your handout. Yeah, just plain mercury metal, which is a very vague term because for anyone who may still have a mercury thermometer, when we think of metal, do we think solid, liquid, or gas? We usually think of a solid, okay? So since this is still mercury, we still call it a metal because where's it located on the periodic table?
Transition metal.
So that's why we call it a metal, because it's in the same category as transition metals in the D block, okay? So then what we see happening, if this breaks apart, because this is a red powder, so something must have changed on this side. So this red powder gets broken apart. So what is possibly left over from that compound?
The oxygen.
Okay. And then as we look at this, how many of you would say that is now written correctly? Does anyone think we don't need to erase anything? Is there something we need to change with this reaction yet? There is. And what would that possibly be? Say that again. Why are you right? Oh, did you say in parentheses? It has something to do with the number 2. No, not in parentheses. No, it's not a superscript or an exponent. Oxygen is a diatomic element. So when it is written by itself, what must you do?
Add a 2.
You put a 2 behind it because, again, hydrogen, nitrogen, oxygen, all of the halogens, those are diatomic, except for astatine at the very bottom, because that is a metal or a solid. Okay? So now, what do we see for elements on both sides of this reaction?
There's 2 oxygens.
Okay, so what do we see for elements?
Mercury has a charge of +2.
Well, we see mercury. That's on both sides. What else do we see? Okay, we see oxygen. Okay. So how many mercuries are on the left side?
2.
There's 1. We got 1 written here. How many mercuries are on the right side?
1.
Just 1. How many oxygens are on the left?
1.
How many oxygens are on the right?
2.
Okay. So keep in mind there are 1s in front of each one of these compounds. So there would be 3 horizontal blanks that all have 1s in front of them because we have not changed anything yet. Okay. So how can we get this to balance out? Well, the mercury is balanced. The oxygen, there's 2 on the product side and only 1 on the reactant. How do we change this number here to get 2 oxygens on this side? You're going to multiply it by 2. And that doesn't mean you can't, don't do this. Don't do that. Okay? Because when you do this, you are changing the formula that you started with. You can't do that. Then that's just incorrect. That would be like some of you golfers maybe doing this. I'm going to add up my 2-hole score here, and wow, I'm a good golfer. Man, just think if you could turn your scorecard in like that every time. We don't have any golfers in here, do we? All right. Okay. So we do. All right. So where would the number 2 go for what we are trying to accomplish here? Okay. So we put it here. And what is a distributive property? What does it mean to distribute? You multiply across. So what is 2 times 1 for mercury?
2.
Okay. What is 2 times 1 for oxygen?
2.
Okay. So our oxygens are now balanced, but now our mercury isn't. Okay. So we can put a large number 2 there. And what is 2 times 1?
2.
Is everything balanced now?
Yes.
Yes, it is. So what numbers are we going to put in this horizontal blanks or lines?
2, 2, 1.
Okay, it was a 1, we put a 2. It was a 1, we put a 2. This one was a 1, and it stayed as a 1. So we just label that as 2, 2, 1. Front row, do we understand? Back row. Middle row. Okay? Go ahead and we'll go back to this. Okay. So what would happen is that he measured both products, this liquidy or metallic-like substance, the mercury, and then it gave off oxygen as well. So what he started with will be the same as what he produced on the right side, because remember, that is talking about this, a conservation of mass. We illustrated that yesterday. Okay. So, and I don't know, the author chooses to say this. Experiment was set for what we now consider as modern chemistry. And sometimes what can happen is what we learn in chemistry can be transcribed and used for human anatomy and physiology. Okay? The reason that we would say that, okay, is how many of you, if you don't mind sharing, have had to have an operation? And in that operation, you're given a type of gas that maybe the surgical technician, I don't know if it's a nurse or a surgical technician, they probably have a type of mask and they say, breathe this, and then you're sleeping in no time. Does that sound from, if you don't mind sharing? Otherwise, don't raise your hand if you don't want to. Okay, so for those of you who did that, does this sound familiar? So when we look at what we learn from modern chemistry, this compound called halothane, okay, is a type of gas that you can inhale, and when you inhale that, you lose consciousness. So then, upon losing consciousness, a surgeon can open up your body, can pull teeth, can do many different types of, if you want to call them operations, and do that pain-free. Of course, well, and there might be some pain when you wake up again, but just the idea of being able to essentially crack the human body open and fix what's wrong. That is, we can owe that to modern chemistry. So sometimes some of these sciences do overlap. Okay. Keep an eye on the time here. So as we look at this, okay, let's do what this is actually illustrating. It says nickel 2 chloride is added to sodium hydroxide. So we're going to stop with that for right now. Okay, so nickel 2 chloride. How do we write that out? What is the symbol for nickel? Okay, what is the chloride ion? Okay, then do we want to, maybe this compound is complete, just like this one was. Do we go further, or do you want to keep going in what the statement is saying? Yes.
Is it in the handout that we're doing?
No, this is the very last thing you wrote down in your handout. Okay? And what we're talking about is this right here. It says nickel 2 chloride. So there's our nickel and our chloride. And it's added to sodium hydroxide. Okay? So, what is sodium? Na. What is the hydroxide ion? I mean, yeah, you have these tools at your disposal. Please use them. Okay? So these are our two reactants. Can we proceed with this? Yes? No? How many say we're ready to go to the other side of the reaction? How many say we need a little bit more work to do on the right side? Okay. How many of us are just soaking this up like a peripherin, which peripherin means sponge. We're just soaking this content up. Is that what we're doing? Okay. All right. So for the 4 individuals that said we're not done, what must we do to change this? Because what does this say? It says nickel 2 chloride. So what's the charge of the chloride ion? What's the charge of the chloride ion? -1. What's the charge of that? What can nickel have for a charge?
+2 and +3.
Well, how do we know which one to use? Because the Roman numeral also has 2. This is mercury, I understand. But it says nickel 2 chloride. So that's +2. That doesn't add up to 0. So what would we need to do?
Divide by 2.
Divide into 2, your least common multiple. Because if we divide by 2, that's right. Now we got 1/2.
Like, I meant like we have to put the 2
Okay.
on top of it.
Right. Okay. So it goes on top. I agree. So then we had -1. So the 2 goes on top. What's 2 divided by 1?
2.
Okay. Now, what about this sodium hydroxide? Is that complete? What's the charge of the hydroxide ion? -1. What's the charge of sodium? +1. Does that add up to 0?
Yes.
Yes, it does. So I can't remember if it says anything. So it says new products are formed. Okay? So these new products, it means these are going to switch. It's like switching dance partners. Okay? You're out on the dance floor, and here's the guys, because they're always positive. Here's the gals, because they're always negative. Am I wrong? No. Who thinks that's right? Okay. But I'll put a disclaimer out. My apologies, ladies. That's not how this goes. I just like to see if some people are listening or paying attention. And we certainly are over there, and some in the back row. Yep. So what this means is we split these in half. Okay? This is one of the I don't want to say traits, that's not the right word I'm looking for, not tools. One of the exercises, you have to be able to do this type of a problem. In other words, complete this equation. So, pick a positive ion. any positive ion that you see here. Okay, so nickel is certainly a positive ion. The charges will not change. So can nickel bond to sodium? No, it cannot, unless there's something like another negative ion in there, and it's something that you probably have in your fridge and in your freezer, okay? Because we know, I like throwing this little bit of information in all the time. What ion is that? Carbonate, okay? Right now, this is something that, again, remember we talked about how physiology can overlap with chemistry, which it does. This is a mechanism that keeps your blood at a fairly neutral pH level, because if it doesn't, there would be lots of things wrong in our body. Okay? This mechanism right here is known as hydrogen carbonate. But, yes, but we said that two positive ions can't bond together. Well, how's this possible? We see two positive ions next to each other. Because sodium's +1, hydrogen's +1, because they're both in the same column. And then carbonate has a -2 charge. So you can have two positive ions next to each other, providing you have a negative ion to hold that together. But you just can't have sodium and hydrogen next to each other. You can, it's called sodium hydride, but that is, again, an upper level chemistry application, and we're not going to do that. But this is something that you have in your fridge or freezer. What might be something that you have in there to keep things fresh? It's probably in a gold box, and it has a depiction of a strong arm, not this strong arm, but a strong arm with a hammer on it.
Arm and Hammer. Baking soda.
Arm and Hammer, but it is called baking soda. This is baking soda right here. It's called, if this was hydrogen carbonate, we put the sodium ion on here, we call it sodium bicarbonate. Baking soda. All right. So yes, you can have two positive ions bonding to each other, providing you have a -1 to do that. Okay, so what would the nickel bond to on this side? It has to be negatively charged. It's not going to bond to the nickel again because it's already bonded to that on this side. So what is negatively charged that we can put on this side? We can put the hydroxide over here because it is negatively charged. Okay? Then what is another positive ion? We got the nickel done, so that's done. This is done. So what's another positive ion that we have? Can someone tell me a positive ion that we see? Which one? Sodium. Okay? So we've got some sodium here. So now we've got that taken care of. So what's the only thing left that that sodium can bond to? The chlorine. Now, don't do this. Okay? Just because there is a subscript on this side, it doesn't mean that it's always going to go to the right side. Okay? Because we needed that 2 to balance out the compound. Remember, yesterday we talked about this method. You did that in last semester as well. I mean, maybe it isn't quite right. It was supposed to go around the 1.
Cross multiply.
Yeah, it's the butterfly method. Okay? You can also use that here, although I missed the target. Okay? So this 2 doesn't always go over here. I mean, it might, but if the charges don't change, is there anything we need to do on this side? And if we don't know, let's put our charges in there. Okay? Hydroxide is negative what? Okay? It was negative 1 over here. It's going to be negative 1 over on this side. What's the charge of nickel? Okay? What's the charge of the chloride ion? Negative 1. What's the charge of sodium? Okay? So as we said, these charges, they're not going to change from one side to the other. Okay? So is this side complete now? No, it is not. Because these charges add up to 0, but these two don't. Okay? This is why writing those compounds that we did last chapter is now so important, so we can do that in this chapter. Okay? So what's your least common multiple between 1 and 2? Okay? So we put that number on top. What is 2 divided by 1?
2.
Okay? We'll come back to that. What is 2 divided by 2?
1.
And we've got 1 there. But we cannot write this like this, because that would be incorrect. Because what does one hydroxide ion has a charge of negative what? But doing our math tells us that we need 2. So if this hydroxide ion has a charge of negative 1, how do we illustrate having 2? Because this is what the math tells us to do. What did we do last chapter if we had 2 subscripts next to each other? In other words, like this. If we had the nitrate, we want 2 of these. Okay, we got to put that in parentheses. So what do you suppose we got to do here? We got to put that in parentheses. Okay? So again, some of those same skills that you've learned throughout this semester, they don't just go away. We still continually use that. Okay. So, who would like to come up here and balance this? Then you don't have to listen to me. Nobody? Okay, I guess, sorry for those of you who tune in later. I guess you have to listen to me. All right. So what elements do we see on both sides?
Nickel.
We've got some nickel. What else do we see?
Sodium.
We see some sodium.
Chloride.
We see the chloride ion or chlorine. Okay? Are there any other elements?
Hydrogen oxide.
Okay? We can do oxygen. Is that it? Hydrogen. There's actually a shortcut that you can take for this, but we're not quite ready to understand that yet. Okay, so how many nickels are on the left side? Just 1. How many nickels are on the right side? Okay, how many sodiums are on the left? How many sodiums are on the right? How many chlorides are on the left? How many chlorides are on the right? How many oxygens are on the left? Okay, careful. How many oxygens are on the right? Okay. Very important that you try to catch this the first time. Why is there 2 oxygens? Because there's nothing written after this oxygen. It's in parentheses. You have to distribute that too. Okay? Hydrogens left.
1.
Just 1. How many hydrogens are on the right?
2.
Okay. So looking at this, we see 33% of that, or no, 40% of that is balanced. 3 out of 5, isn't that 40, or is that 60%? That's 60%. Okay? So where might be a spot that we could put a large number? In front of these isn't going to help us for sure. But we see chloride is out of balance, so is hydrogen and oxygen. So maybe let's start with our chloride ion, because we've got two of them over here, and we've only got one over here. How could we change this to get two chloride ions on this side?
Multiply 2.
Okay, so when we say multiply by 2, we put a large number in front, distribute that through the compound. What is 2 times 1?
2.
Okay. What is 2 times 1?
2.
Okay, so that's also 2. Maybe we didn't gain any ground. Our chlorides are balanced. Now our sodium is out of balance. Okay? But we've got 2 sodiums on this side. And how many sodiums are on this side still?
1.
How do we get 2 sodiums over there?
Times it by 2.
Times it by 2. So distribute that through the entire compound. What is 2 times 1?
2.
What is 2 times 1? What is 2 times 1? Okay? So we've got 4 horizontal lines. Okay? Starting from left to right, what would we put for here?
1.
We didn't change anything, so it's 1. What about this blank?
2.
That was a 1, but we changed that to a 2. Okay? Did we change anything here?
No.
We did not. So that is 1. And what about here?
2.
There's still a 2. That is now balanced. It would be 1, 2, 1, 2. Okay. So this is just coming from your handout now. I want you to look at page 3. And how many of you have that reaction done? Calcium plus HNO3 gives H2 plus CaNO3, parenthesis 2. Does anyone have that done? Okay. So is that something you'd want to work on by yourself, or should we go over that together? Okay. I heard ourselves, but and I also heard together. So I'm going to pause this for just a moment. Okay, so we have this equation about 98% done. Okay? What do you see on your paper that is different than what we see here? Okay? Now, hydrogen is by itself. When that happens, you said there is a 2 here. What vocabulary term tells you to do that? We said it earlier in the hour. Starts with the letter D. It's diatomic. It's a diatomic molecule. What else do we see is different?
The calcium and nitrogen.
Okay.
Parentheses with 3.
Right. Because we've got calcium is 0, plus 1, minus 1. The charges will not change. This is now 0. Okay? Plus 2, minus 1. But that 3 automatically comes over here because that is part of that ion formula. We don't just write hydrogen because when it's by itself, remember, it is diatomic. The only time that these subscripts go over to the other side for sure is when they're tied into a chemical formula or molecule. Here's another one. That 4 would go to the other side because it's part of the sulfate formula. What is another polyatomic ion? How about CO3? We talked about that earlier. That 3 would automatically go to the other side. Same thing with phosphate. If this was in a compound, that 4, this 3, this 4, it automatically goes to the other side because it's part of the formula. Okay. So what do we need to change on this side? Okay, so we have to put parentheses 2 here because this has a charge of -1 and we need 2 of them. That math is telling us to do that. Okay. So we've got 4 horizontal blanks, and for those of you who want to work on these, we're running short on time, but it looks to me like we have 1, 2, 1, 1. Then we're done. Is that what you did? No? You don't have these 4? I expect that from a Duke fan. Okay, so I know we get confused. Okay. Now we're on the same page. All right. All right. I mean, that's why they have that big duh. I'm from Duke. That's why that D is on there. But that's not how you spell duh, is it? All right. So we'll continue with this tomorrow. You will have a paper over this where you're balancing these reactions. If you fall, I'm just telling you how it is. If you fall behind, it is really hard to get caught up. Okay? So if you are having problems, whose responsibility is it to ask for help? Ours. It's yours. You are acknowledging that. So keep doing that. Okay, we'll catch up to you next time.